Hello, welcome to this tutorial. In this video, we are going to look at how to build 1D HEC-RAS model, specifically the steady flow model. We are also going to look at inserting bridges on covert. We're going to look at how to insert levees and how to replace existing bridge. So this is going to be the center line or the whole scope of this entire coverage. Um, Basically, we are going to, when we talk about 1D steady flow model, we are basically looking at the water surface elevation and how the water is routed from one cross section to the next cross sections. Also considering all the head losses that go in. So we are going to be covering that in this entire tutorial. It's going to be a combination of multiple videos. So we're going to break them into separate sub-part videos. So it's going to be short and direct. And so just to proceed quickly, we're going to look at the next. So on the first part, this video, basically this is summarizing what we are doing. In this first video, I wanted us to mention that we are going to be learning several steps, and part of the whole model will include how we be able to delineate our streams and also be able to insert cross section using RAS-MAPPER. So we are going to insert multiple cross sections, and at the end of the day, we are going to learn how to insert our bridge covert. Can be a good example. And also we're going to see levy. So this is going to be a good example. So we're going to also see that in the 2D viewer window using the RAS mapper. There's going to be some terrain modification that we are going to do. The terrain modification will be very helpful, helping ensuring that we are able to send the terrain in the right format before we can use them. And I've also linked to some documentation here. It's called the HEC-RAS guides and tutorials that kind of go into detail the 1D steady flow model and what it entails. So I'm just going to quickly bring that up here and just do an overview on it. So the 1D steady flow model has different components. It's called examples that are walkthrough helpful for new users to be able to set up a HEC-RAS 1D steady flow model. And if you look at all the different sublinks or the buttons, we have a guide on how to develop a 1D geometric data with RAS-MAPPER. So basically, this tutorial use an example of a data and being able somewhere in California. It's called the Tolume River near Modesto in California. This tutorial will show basically how we can create new RAS terrain in RAS-MAPPER and be able to add those 1D geometric layers like the cross sections we see here. And I think there are other components that the tutorial covers, and you can see how to edit cross sections and all. So this is a very good start for new users of uh, HEC-RAS or new RAS-MAPPER. And you can see how we also have tutorials on steady flow modeling with HEC-RAS. So you can go in here and see this is another example of data. The project is in Mesquite River at Yosemite in California. You can be able to use this tutorial as a guide to learn how to set up your own 1D model and how to be able to bring in your DM elevation from USGS and also do some analysis on the terrain and create cross sections and run your model and all. You also learn how to assign the Manning's-N coefficients using land cover data. So I'm not going to go into detail into this. I just want to point you to these tutorials here that if you're new to HEC-RAS, it's always good to start from somewhere. So why I try to summarize using examples, these other tutorials and projects available here on the guide will be able to provide solid background and prepare you for more complex 1D model. We also have some on bridge development, and this after before building the bridge, it's always advisable to build your 1D model. then inserting the bridge. So we don't start by inserting bridge before building the model. So we build the whole model starting from scratch. We're able to insert the cross sections, have the streamline, have the bank stations and the flow path. And after that, we can go ahead and make sure the model is good. We've run it, fix all the issue. Then we can go ahead and insert the bridge and also culvert where we have to insert those geometric element or infrastructures. So this is a good example, show you how to insert bridges and how to take care of those elements like ineffective areas to make sure that the model runs and the model is good fit. We are going to cover part of this in the whole tutorial, so I just want to point you to this training. We also have information on bridge analysis, so if you want to learn more um, on how to perform analysis using the HEC-RAS bridge, this is an example data somewhere near Kentwood, Louisiana. So this data can provide will help you to learn how to use HEC-RAS to perform water surface profile computations through a bridge. I'm not sure the study covers scour analysis, but you may be able to learn some detailed scour analysis of these tutorials, and where you can perform some basically starting from water surface elevation. We also have covert analysis. It's very similar to the bridge analysis. You just learn a different way to what we look at when we place covert, especially looking at invert elevations. That makes it unique and different from the covert. So with that, you also learn how to calibrate the steady flow model. You learn how to be able to use HEC-RAS to calibrate steady flow hydraulics. You also adjust parameters and also see the parameters adjusted could be the input flow data that is been inserted. It can also be some of the roughness coefficient. It could be some other parameters that we are going to cover in the video when we do run through the tutorial. So they are good examples, and each of the examples are covering different locations, so are very helpful for you to be able to take advantage of those. This particular example is somewhere uh, in Lewiston Lake near Riverview, California, and there's a good data here to start from. Then we have troubleshooting tutorials that can be helpful to learn how to do some troubleshooting, do any fixes that needs to be done. We're going to see some of those examples, and there's a workshop that you can sign up for, and also to learn how to fix some issues. So this is some HEC-RAS guideline tutorials that have been provided. You can be able to learn how to do 1D steady flow model here. Let's go back to the trade. All right. Um, at the end of the day, we'll be able to cover the entire process of building 1D, the basics of building 1D steady flow model. We're also going to cover how we can be able to insert our bridge and do some troubleshooting. So for the meantime, we are going to look into some basic equations. Now these are the equations that govern the HEC-RAS 1D model, or we can call it the steady flow model. So basically, the equations take care of some parameters, and the first parameter is the water surface elevation. So the water surface elevations are computed from one cross section to the next by solving the energy equation. So we use basically the iterative equation called the standard step method, the SSM. The standard step method basically computes the water surface profile from one cross section to the other cross section while accounting for loss, and that is what we see here. So we have as we move from one cross section SS2 SS1 cross section 1 to cross section 2, we move from cross section 2 to cross section 1, there's always going to be a loss, which is the head loss, which is the HE. Now to compute these parameters, there's a need to understand the transfer function going on here. So we have Z2. Z1 and Z1 should be equal to Z2, but then we have to also account for loss. So we have Z2 plus Y2 plus alpha 2 change in velocity 2 divided by gravitation acceleration. Then we have the same in the other direction, but then we also need to account for losses. It could be loss due to contraction that leads to water being infiltrated or water being not being accounted for. The water could lose momentum or could be ponded somewhere. So we need to account for that hydro energy head loss going on here, which is that difference we see there. So how do we account for those two? Basically, and if I mentioned earlier that the Z1 and Z2 are the elevation of the main channel inverts. So we are using the invert elevations of those channels to use. Um, and then we also have the Y1 and Y2. This Y1 and Y2, they are the depth of water at the cross sections. The depth of water. So we can have the channel here, surface here, and we have the Y1, Y2. So we'll have the first depth and the second depth. And we can see that water, um, how far is it, the difference in the height when you move from this cross section to this cross section. Do we know that? And then we have this change, this one here, where we'll have um, the V2. The V2 here is there, and the V1 are the average velocity. We're talking about the average. Then we'll have over G, we're talking about average velocity, which is the total discharge all over total flow area. So that will give us what we have in this part of the parameters or the function. And we have the same in the same cross section. But however, when we move from one cross section to the other cross section, we have some loss going on that we have to account for. So we need to calculate this head loss to be able to account for the energy balance. And to calculate the head loss, we have an equation that has been set up to do that. This head loss is basically looking between two cross sections, is looking at the friction loss, the contraction loss, or the expansion loss, as I've mentioned earlier. The equation, like we mentioned, has this LSF plus C, and this whole equation account for the discharge width reach length, which is the L. It account for the friction slope between two sections. It also account for the expansion or contraction loss coefficient, and that is the C. The rest of the equations are coming from the water surface elevation we have upstream. And then we also need to calculate the discharge weighted reach length, which is the L. And to calculate that, we need to account for the cross-section reach length. We need to account for um, flow in the leftover bank, flow in the main channel, and right bank, respectively. So you see those information here, which are the flow from all the directions. We also need to account for the average flow between sections for the left bank, so which is a Q. And so we have the channel. LOB means the leftover bank, ROB means the right over bank. And you can learn more about these equations and how they're very useful. But later in the video, we are going to see that calculating the water surface elevation is very important. It helps us to be able to determine some other parameters like the HW over D over time. So that is going to be what we're going to be covering in this video. If you are new to 1D model, I will encourage you to go back to the earlier um, link I shared and learn more about um, the 1D steady flow. And to have a sense of what is happening, you also need to be able to learn about the governing equations, which uses the steady state SSM equations to calculate water source elevation and also determine the head losses and also the reach length. So this is very important, and be able to but in the focus of this video, we are not going to be looking at derivations or equations. We are going to practically look at how to model the 1D model in HEC-RAS. This is a good example where we are going to be inserting about 10 cross sections, and those cross sections we are going to see how to do that uh, from the beginning to the end. So sit tight. In the second video, we are going to look at some other aspects of the tutorial. But this is just the introduction, and you need to have some basic background on hydraulics and hydrology. And if you want to learn more about hydraulics and hydrology, I will encourage you to start from this training guide. And I'll see you in the next tutorial, the next video.